Hello everyone. So we'll see a question that was asked in CSIR NET December 2023, and the question ID is 704065. Okay. So the question says let f and be a sequence of function defined on this interval, and f and x is defined in this way. Okay. So what can you say about fn? So option O says Fn converges pointwise on this interval. Fn converges uniformly on complex subset of this but not on this. Fn converges uniformly on this but not on this. Fn converges uniformly on this. Okay. So come back to the solution. So yeah, solution. So here we'll use a theorem. So I just stated the theorem here. Okay, so theorem. If G is continuous on this interval and fnx is of this type where x belongs to close 0. Okay, then the sequence that is fn is uniformly convergent on this interval if and only if g1 equals to 0. Okay, so by using this theorem we can directly say that okay, fn converges uniformly on this interval. Okay, fine. Here fnx equals to so we can write it as g of x where gx is okay. Here gx is continuous on this interval and g1 is nothing but log of 1 plus root over 1 by 2 log of that is 2 by 2 that is log of 1 which is nothing but 0. Okay, so by using the above theorem we can say fn is uniformly convergent on closed interval 0 comma 1. Okay, so option 4 is true. Fn converges uniformly on closed interval 0 comma 1. So from this option 1 is also true since it is uniformly convergent, so obviously it is pointwise convergent, and option 2 and 3 are false. Now we'll see the proof of the theorem that we've used here. Okay, so proof. Okay, so what the theorem says, if g is continuous on closed interval 0 comma 1 and fnx is of this type x to the power n gx where x belongs to closed g1, then the sequence of function that is fn is uniformly convergent on this interval if and only if g1 equals to 0. Okay, so how do we prove it? Okay, so let fn be uniformly convergent to the function say f, alright, on this interval, then f is continuous. Why f is continuous? Why? Since fn uniformly convergent to a function f, then this is a very well-known theorem that if a sequence of function uniformly convergent to a function f, then the limit function that is f should be continuous. Okay. Okay, fine. So what would be the limit function fx? Okay, there are two cases. If x lies in close 0 open 1, then this is 0. Why? Because if x lies in close 0 open 1, then limit n tends to infinity x to the power n equals to 0. Okay, what about the point x equals to 1? At the point x equals to 1, fx would be g1. Okay, fine. But by the continuity of f, we have f1, which is this. So therefore g1 has to be 0. Okay, so first part is done. Now second part. So conversely let g1 equals to 0. So now we have to show that claim fn is uniformly convergent on this interval. Okay, so how do we show this? Okay, fine. Okay, if x lies in close 0 open 1, then limit n tends to infinity fn x, that is limit n tends to infinity x to the power n gx is 0 clearly. Why? Since limit n tends to infinity x to the power n equals to 0. Okay, and fn 1 equals to 0. Why? Since g1 equals to 0. Fine. Okay, so what do we have? What we have now, we have fn converges to f pointwise. And what is f here? And here f is 0. Okay, now we have to check the uniform convergence. Alright, so for this we now use Amend test. Okay, so for uniform convergence we will use Amend test. Okay, that is Amend supremum x belongs to close 0 close 1, and okay, so this will be supremum of x belongs to this close interval 0 1 and fn x. Since the limit function is 0, that is fx equals to 0. Okay, now further we can write that is x 0 x belongs to close 0 1, and this is x to the power n gx. Okay, fine. Okay, here fn is continuous on close 0 1 close interval 0 1, and therefore and therefore Fn is bounded on this interval. Why? Because we know if a function is continuous on closed interval 0 comma 1, so it is uniformly continuous, and also it is bounded on this interval. Okay, so this is also a well-known theorem. Okay, and since it is bounded on closed interval 0 comma 1, so the supremum is at n. Therefore supremum is at 10. Supremum is at 10 at some point say a, say in closed interval 0 comma 1. Fine. Okay, since g1 equals to 0, okay, so it follows that the supremum, so the supremum of Fn is attained at some point in this interval. Fine. Okay, so now Fmn that is a to the power n and g of a for some a which is belongs to this interval, and if we take n tends to infinity, okay, we can write it as now limit n tends to infinity mn 0. Why? Since limit n tends to infinity e to the power n equals to 0, since a belongs to these intervals. Okay, so from the mn test by m test, Wester m test, we can say Fn is uniformly convergent on this interval. This is the proof. Okay. Yeah, the proof is a little bit lengthy, but if you can remember this theorem, so the question is easy, and we can directly use this theorem to solve this question, and the question will be framed in different way also. Okay, overall the question is interesting. So yeah, thank you.